Hello and welcome to my ELS 2021 talk, a Tangram puzzle solver in Common Lisp. I am Michael Wessel. Let me start by giving you a brief outline of my talk. First, a little disclaimer. This is really a demo talk about a CLIM application, so you can expect a video of the program, seeing it in action, and also we will discuss some Lisp code. And please do not expect any deep theoretical insights like computational complexity results or what have you, but I can give you some practical insights into these problems. So this is really a fun recreational spare time project, and it is not associated with my employer in any way. The program really has a bit of a history. It was originally written in 2003 and I reactivated it now. So why did I do that? A couple of reasons. First, to get back to Lisp really, one question I had for myself is, would I still be able to maintain and extend my Lisp code from almost 20 years ago? And the 2003 version of the program also had some bugs and severe deficiencies, and then I really never got to sort these out back in the day, so I wanted to finish what was started back then, and I can tell you that it is performing much better now. I also wanted to catch up with the Lisp community and check out what's going on recently. That's of course always good motivation for a paper. Last time I contributed something to the Lisp conference was 15 years ago. Also because of a recent book that really fascinated me, and I'll give you the book tip at the end of the talk. Tilings and tessellations have always fascinated me. Here are two well-known examples. A Penrose tiling on the left and the set of standard Tangram tiles on the right. The Penrose tiling extends infinitely, whereas the Tangram tile set is of course a finite tiling. The Penrose tiling is particularly interesting. It has 5-fold symmetry. And it is actually aperiodic. There is no simple translate and copy periodic pattern that can be used to extend it infinitely. If you're curious to find out what this has to do with the state of metacoid quasi-crystals, then have a look at my book tip at the end. The Tangram puzzle is an ancient Chinese game, and the standard Tangram tiling is shown here. It is a so-called dissection puzzle. For reasons of decidability, we are dealing with finite tilings only here. Other inspiring examples of tilings and tessellations are of course given by the inspiring artworks and masterpieces of Dutch graphic artist M.C. Escher that many of you will know. But back to our Tangram puzzles. Even though it's quite an ancient Chinese game, there's still a lot of recent interest in them. There's a lot of business around them on the internet. That also means that you can easily find Tangram problems. There are lots of books and problems to be found online. For example, here's the famous Tangram bat problem, and we will show later how to use our solver application to solve it. I would now like to show you how to use the application to construct a Tangram problem, so let's fire it up. Alright, so let's have a look at the Tangram CLIM application. Before we can solve a tiling problem, we first need to construct one, and for this we are using the problem editor. First we select a set of construction tiles from the list of available tile sets in the bottom left pane. In this case, the Tangram tile set. The set then shows up in the editor on the right, and we can start constructing a problem using drag and drop on tiles. Note that all these objects are instances of clause classes and hence CLIM presentations. As such, we get automatic presentation highlighting and also CLIM computed context menus. We can rotate and reflect tiles. An active grid is used. The snap-in grid positions are aligned to previously placed tiles, so this makes construction of problems very easy. The red vertex of each tile is a reference point for rotations and reflections. It can also be changed to another vertex of the tile. Once the problem is complete, we hit the problem button. This records the outline or silhouette polygon of the arrangement and stores it in the problem library. Note that the concrete tile arrangement is not stored as part of the problem, only its outline. Hence, no cheating is possible, At the same time, we are making sure that there is an exact geometric solutions in terms of exact angles and scales. Now that we have seen how to construct a Tangram problem using the editor, let us quickly go over the rules of the game. It's very simple. Each tile must be used exactly once. The silhouette outline problem polygon must be partitioned completely by tiles, such that there is no remaining space left between them, and of course there cannot be any overlaps between tiles. Tiles can naturally be translated, rotated and flipped over, which means they can be reflected. For example, this one here is a reflected variant of this tile, and if you compare this to the possible rotations around 45 degrees, which are listed here at the bottom, you see that the reflected variant is not one of its rotated variants. So the reflected variants of each tile, modulo congruency, constitute a tile type, and only one reflected variant of each tile type may be used in a solution. We are using geometric search to solve the tiling problem, and this is quite intuitive. This is illustrated here. Starting from the problem polygon at the top of the search space, we are computing successor configurations by aligning a remaining tile with the current configuration polygon. Of the so generated successor configurations, we are selecting one and proceed further down in the search tree. We now subtract the polygon of the aligned tile from the configuration polygon and consider the next unused tile. Note that the configuration is potentially split into multiple components as shown here. A configuration is hence a set of polygons representing the remaining area that still needs to be covered. Alright, let's see the solver in action now. To start the solver, simply select a problem from the list of available problems and then hit the Solve button. If the Show Syncing checkbox is enabled, it will visualize the search process as shown here. After 6 minutes, it finds the first solutions, and the solutions show up in the Known Solutions pane. If the Show Syncing checkbox is disabled, it takes about 3 minutes for the first solutions to arrive. Note that it already found some permutations of the official solution. Usually, each Tangram tile needs to be used exactly once. However, we can also instruct the solver to allow for multiple copies of individual tiles. This is illustrated with this run. Note that solutions show up much faster in this mode. It is also interesting to see the multitude of possible solutions in this mode. We can simply stop the solver at any time using the Stop button. I'm sure you'll all love to see some Lisp code, so let's have a look at the find covering main function. It takes as input the problem polygon, which is a list of polygons, and the set of tile types, which is a list of lists of polygons. As explained, each tile type represents the tile and its reflected variants. Then we are using a local variable solutions here to keep track of the solutions found so far, and the main search is performed by this local function doIt. The current configuration is this variable polygons, which is a list of polygons. As explained, a configuration might be split into multiple components. So these are those multiple components, and the remaining tile types are in the tile types variable. We also keep track of the history of the tiles, how have they been used and how have they been aligned. First thing then in the local doIt search function is we check if a solution has been found, and in the goalp predicate this is of course the case if there are no polygons left to be covered, so polygons is empty, and either we must have used all our tile types because each tile type must be used exactly once in a standard problem, or we are allowed to use less tile types. In this case, we are fine with that solution as well. So if we found a solution, then we register the solution by pushing it onto our list of solutions together with the tile types. These are the transformed polygons and the construction history, so we can reconstruct the arrangement. And unless we requested all solutions, we can then return from the function with the solution found, because we are good with one solution. Else, our current configuration polygon is not a solution, and hence we need to expand the search space. We do so by computing successor configurations. For each component polygon in the current configuration, and for each tile type and its reflected variants, we are considering all possible alignments of the tile with the component polygon. If a perfect match has been found, it means that the tile perfectly fits the component polygon, and hence that component polygon can be removed. Else, we have created a new successor configuration polygon in which the aligned tile has been subtracted from the component polygon. Both cases, together with their heuristic scores, are kept in separate lists: perfect alignments and alignments. For a given configuration, we hence first compute all possible one-step successor configurations and put them into lists. Next, we are sorting these successor configurations in descending order with regard to their heuristic scores for further consideration and expansion of the search space. In the list of computed successor configurations, we always prioritize the perfect alignments over the imperfect alignments. Each successor configuration has 5 components: the heuristic score, the transformed tile polygon, the computed successor configuration polygon, the original polygon, and the remaining tile types. There are 2 cases. If the successor configuration is a perfect match, it means that the aligned and transformed tile polygon completely matches and resolves the original component polygon. In this case, we can consider this polygon done and only proceed in our search with the remaining polygons. Otherwise, we need to append the successor configuration polygons to the remaining polygons and continue our search with a larger set of polygons. But how do we actually compute a successor configuration polygon for a given tile polygon and a component polygon? This is illustrated here. We would like to find a transformation that transforms the tile polygon onto the inside of the component polygon, as shown here. Then we can simply subtract the tile polygon from the component polygon if it happens to lie on the inside and touches the component polygon from the inside. To compute this transformation, we are using all possible pairs of line segments between the tile polygon and the configuration component polygon. We are using the pair of line segments to compute a rotational angle for the tile polygon, then rotate the tile polygon around that angle and also translate it onto the configuration polygon. If it then happens to lie on the inside and touches the configuration polygon from the inside, we can subtract it. It might also be the case that it happens to lie on the outside as a result of the transformation, or that it overlaps, in which case it does not represent a valid successor configuration. Also, it may be the case that the transformed tile polygon will be completely congruent with the component polygon, in which case we have found a perfect match. So let's talk a little bit about the geometric heuristics that we are using in the scoring function. Heuristics are essential in order to make the search succeed. One is tile area. A heuristic such as biggest first makes certainly sense, because the bigger the tile, the larger the reduction in remaining space to be covered, hence reducing the branching factor of the search early on. Another very useful measure is the compactness of a successor configuration polygon P, or of a shape P. It's defined as the circumference of the shape over the square root of its area. There are a couple of examples given here. For the circle, it's about 3.5, for a square it's 4, and for something like a U-shaped polygon, it has a very high compactness value of 5.3 here. So the idea is, the smaller the compactness value, the better. Given that we have identified a number of interesting geometric characteristics such as tile size and compactness that we would like to use in our scoring function, the question then is, how do we combine these different characteristics into one score such that we can use the sort function, right? So rather than putting it all into one score by using a weighted sum, which is difficult if these values are not normalized, right? For example, there's no upper or lower limit for compactness, for example. So these scores might overlap in non-intuitive ways. We rather use a lexicographic ordering of criteria ordered by importance of the criterion. So tile size being the most important one, then negative compactness, followed by less important criteria, and then we just use lexicographic ordering on these complex scores. So enough theory for now. Let's demonstrate the effectiveness of the heuristics by performing some experiments with the solver. To demonstrate the effectiveness of the heuristics, we make an experiment and simply randomly permute the ordered list of successor configurations rather than processing them by descending score. As illustrated in the listener, the reorder function simply permutes its input, so we are applying it to the ordered list of successor configurations. So, with the result of the sort and hence of the heuristics being destroyed in that way, the program now clearly displays a much more erratic search strategy. The initial location of the blue triangle will result in a lot of trashing, and no solution will be found due to a bad early placement of a tile, illustrating the effectiveness of the heuristics. The application also offers load and save functionality. Here I'm loading a problem from disk rather than constructing it with the editor. There are hundreds if not thousands of Tangram problems on the internet and in various Tangram books. This one is the so-called bad problem. The bad problem can be solved in about a minute if show syncing is disabled. With show syncing enabled, as shown here to illustrate the search process, the program takes about 3 minutes to find the first solutions. Note that it again found some permutations. Just for completeness, let us also load the third problem discussed in the slides. That looks a little bit like a broken heart or whatever. And let's see a run of the solver on this one. So that only takes 15 seconds or so. So that's really fast. That's not a problem at all for our Tangram solver. And there you go. The default scoring function considers the tile size the most important criterion and the compactness of the successor configuration the third important criterion. What if we only consider compactness? Let's change the scoring function. Since the lower compactness value is more desirable, we have to negate the compactness score here. So rather than maximizing the compactness value, we minimize it. So, with the compactness score being minimized, we can see that the solver will now try to find matching tiles that nicely fit in the polygon corners, and that tile size is not a consideration anymore. However, the strategy fails. It is also quite interesting to investigate what happens if we maximize compactness. So let's change the scoring function again. Here we no longer negate the compactness value, and the value is then being maximized by the sort. If we start the search again, we can now see that the solver is deliberately investigating configurations that are showing gaps between tiles, and over time corridors around tiles start to form, as I'm showing with the mouse pointer here. This is a clear indicator of high polygon compactness. This setting might actually be good in another application domain, for example for designing shopping mall floor plans, but it is not desirable for solving tiling problems. To wrap up the demonstration of the effects of different heuristics, let's undo all the changes and revert the scoring function back to its original form. As demonstrated earlier, with the scoring function back to normal, The solver finds the first solutions to the problem again after about 15 seconds, so all is good again. For the final demo run, we are showing one more time what kind of solutions are found if multiple copies of tiles are permitted. Here you go. In addition to the geometric heuristics just discussed, we found two more highly effective optimization techniques. The first one is remove congruent successor configurations. Congruent successor configurations occur naturally because tiles have rotational symmetries, and there are congruent tiles also, for example the big red and the big green triangle. There is no need to explore the resulting configurations repeatedly in the search. We can hence reduce the branching factor considerably. The second technique relies on common sense. Clearly, if a component polygon has been produced that is smaller than the smallest remaining tile, then no solution can be found because no remaining tile will fit into that hole. Hence, we can backtrack early. Let us quantify the effectiveness of the various discussed optimization techniques on the standard Tangram problem and the bad Tangram problem. First, with the scoring function disabled, none of these problems can be solved within reasonable time. Hence, for each problem, we consider three settings with regard to optimizations A and B. Optimization A is a branching factor reduction by removing congruent successor configurations, and B is a fail and backtrack early by realizing dead-end configurations if the smallest component is too small for any remaining tile to fit in. With A and B enabled, we can solve the standard problem in 3 minutes. If we disable B, it takes 6 minutes. With both disabled, it already takes 27 minutes. For the bad problem, it's even more interesting. It takes 1 minute with both optimization enabled, 2.5 minutes if we disable B, and 45 minutes with both optimizations disabled. Note that these times are recorded with show syncing disabled. This shows that the additional optimizations A and B together have the potential to reduce problem size by an order of magnitude. So it's time to wrap up this presentation. My initial question was, or one of my initial questions was, would I still be able to maintain and extend my Lisp code from almost 20 years ago? I can now confidently answer this question with yes. And Lisp was fun to work with again after many years of absence. I think Lisp code has really good code maintainability due to concise, precise, semi-formal small computational units in the form of functions and methods. The program is running much better than in 2003 by now. I feel that for now I finished what was started. The search space of the problem is certainly very large. Getting the initial positions of the first two tiles right is essential because otherwise backtracking to them to revise their positions won't happen for a long time, so the heuristics are really essential. Without heuristics, no solutions can be found within 24 hours. Future work will focus on porting this program to other Common Lisp implementations such as Steelbank Common Lisp, and I would also like to investigate MacClim and further tiling problems like the aforementioned Penrose tilings. Also, more optimizations could be investigated like random restarts. I would like to point you to my GitHub repositories under this address here. You will find some reusable Common Lisp modules there, such as the geometric substrate and also a persistence module similar to Pickle for Python. So I think there might be some reusable functions and classes for you. Also, the source code and executables for Windows and Linux 32 bits for Tangram are available there. So yeah, give it a try. Try playing and tweaking the heuristics and see what it does for you. Currently it uses LispWorks 6.1, but it also works with LispWorks 7.1, and it requires Klim, of course. Many thanks to Rainer Josvig or LispM, who actually managed to run it on one of the new M1 Silicon Macs using LispWorks 7.1, and for tips regarding application delivery. Thanks, Rainer. To conclude this talk, I still owe you that book tip. This is a book that really fascinated me and that motivated me to look into tiling problems again. The Second Kind of Impossible: The Extraordinary Quest for a New Form of Matter by Paul Steinhardt. If you have a passion for physics, tiling problems, and want to know what this has to do with Penrose tilings and quasi-crystals, then I'm sure you will love that book. Thank you very much for attending my talk, and now it's time for questions.